1 minus ratio is 1 by 6, it is less than 1. So by simplification we can see that 1 by 6 upon 5 by 6. So what is the answer? 1 by 5. And definitely this is not AB, that means 1 by 2. Okay, so this was required series to show this example. Slide please. Next, in the next example we have to show that sigma an by bn may converge to something other than a by b even when a is equal to sigma an, b is equal to sigma bn, and no bn equal to 0. So let us see, or let us consider with the same example. Here we have to show sigma an by bn. Sigma an by bn may converge. So what we can take? Can we go with the same examples? Consider an is equal to 1 by 2 raised to n, bn is equal to 1 by 3 raised to n, or let us change the notation here. Consider an is equal to 1 upon 3 raised to n, an is equal to 1 upon 3 raised to n, bn is equal to 1 by 2 raised to n, and an by bn we can see that it is 2 by 3 raised to n. With this term, which is less than 1, this series sigma an by bn is convergent, and you can check that it is not exactly a by b. So try it yourself. Let us see slide. The next example, if sigma an converges and an is positive for all n, can anything be said about sigma 1 upon an? So here given that sigma an convergent and therefore limit of nth term is 0. What is the limit of the 1 by an? See, here sigma an is convergent. This implies limit n tends to infinity an is equal to 0. Now we have to consider sigma 1 upon an. Since limit n tends to infinity 1 upon an is equal to obviously infinity, this series is divergent. Okay, keep in mind, if the series sigma an is convergent, then simply a series formed by its reciprocal is always divergent. Okay, slide please. So here we have one constructive examples. Make up an infinite series whose sum is 1. So that we have to define. We have actually we have to construct 3 sequences with 1, minus 3 and 0. These are 3 examples for us. So for 1, actually up to now we know the convergent geometric series a plus a r plus a r square and so on, plus a r raised to n minus 1 and so on. We know that if r is less than 1, then its summation is if mod r less than 1. So let us try to correlate these two terms, 1 and a upon 1 minus r. So choose a is equal to 1 by 2, r is equal to 1 by 2. we can see that this term, if I write 1 by 2 here, if I write 1 by 2 here, then this ratio is 1. So with first term a is equal to 1 by 2 and ratio is equal to 1 by 2, the series form whose answer is 1. So how we can write? Let us see, 1 by 2 plus 1 by 2 whole square plus 1 by 2 whole cube and so on. This is the series whose answer is 1. Okay. Same thing we have to do for this minus 3. So try to concentrate on here. Choose some number a is equal to something as we have done here and here, such that this ratio a upon 1 minus r will be minus 3. Let me give you one of the choice. If we choose a is equal to, suppose, minus 3 by 2 and ratio r is equal to 1 by 2, then this choice will work for the geometric series whose answer is minus 3, right? Now for let us consider for 0. So is it difficult task to make a series whose sum is 0? How we can consider this? Definitely we can make a series whose answer is 1. Then you can just add one more term as minus 1 with that series and we have answer as 0. So this is required series. So many series you can write whose summation is 1 and add more one term minus 1 and the answer is 0. Slide please. Next. Here now we have to see non-decreasing partial sums. Suppose that sigma an is an infinite series with an positive for all n. Then each partial sum is greater than or equal to its predecessor, because Sn plus 1 is equal to Sn plus an. So we can consider that S1 is the smallest term, then it will increase to S2 less or equal to S3 less or equal to Sn less or equal to Sn plus 1. So here the sequence of partial sum in case of positive terms, it is non-decreasing partial sum sequence. Since the partial sums form a non-decreasing sequence, the non-decreasing sequence theorem tells us that the series will converge if and only if the partial sums are bounded from above. Next. So let us write down that theorem 6 as a corollary in the case of series. A series sigma an of non-negative terms converges if and only if its partial sums are bounded above. Next. Let us see the theorem which is known as integral test. Let an be a sequence of positive terms. Suppose that an is equal to f of n, where f is a continuous positive decreasing function of x. For all x greater or equal to n, where n is positive integer, then the series sigma an and the integral n to infinity fx dx both converge or both diverge. So here in this test, series and integration both simultaneously converge or both simultaneously diverge. Here let us see the geometry for this. Tabletop please. Here I have drawn one function which is continuous, decreasing and positive. Also it has the property that fn is equal to an. So for the first value a1, and it is f of 1. This is what actually f of 1 or a1. For 2, here it is the point. For 3, here it is the point. Similarly for n minus 1 and an plus 1. Now for this geometry, we can see that region of this first rectangle, here breadth is 1 and length is a1. So area of the first rectangle strip is a1. For the second, area is a2. Similarly, an minus 1 and an. Now in this case, we can see that integration from 1 to n plus 1 fx dx is less or equal to, because the integration of this region 1 to n plus 1, that will start from this 1 to n plus 1 and from this region, and we have chosen rectangle which is larger than the required area. So definitely we can write integration from 1 to n plus 1 fx dx is less or equal to this first a1 plus a2 plus a3 up to an. So by geometry we can conclude that the integration 1 to n plus 1 of fx dx is less or equal to sum of first n terms a1 to an. Let us call that this is equation 1. Now same thing again in different manner, same geometry. Now we will consider smaller rectangle from the region covered by integration of fx. Here we can see that the first rectangle is a2, second is a3 and so on up to an. So integration from 1 to consider as n. We can see here integration from 1 to n fx dx. It is larger than this because we have taken smaller rectangles a2 plus a3 plus up to an. This is called equation number 2. So let us see again equation 1. Equation 1 says that integration 1 to n plus 1 fx dx less or equal to a1 plus a2 plus an. Here it is starting from a2 plus an. So let us add both side a1. When we add both side a1, it looks like a1 plus a2 plus up to an less or equal to a1 plus integration from 1 to n fx dx. Let us see both equations simultaneously. It looks like this. So integration 1 to n plus 1 fx dx less or equal to a1 plus a2 plus an less or equal to a1 plus 1 to n fx dx. Now this inequality ensure that when this integration is convergent, definitely this is same thing. So this is also convergent, and therefore this integration partial sum goes to some finite limit, and therefore we can say that this integral is convergent if and only if this series is convergent or sequence of partial sum tends to some finite limit. If this is finite, then this is also infinite. Therefore both converge together or both diverge together because of this inequality. Slide please. A very good example of integral test is P series. That also we have to remember for frequent use. The P series is known as sigma 1 upon n raised to p is equal to 1 upon 1 raised to p plus 1 upon 2 raised to p plus 1 upon 3 raised to p and so on. We will show that this P series converges if p greater than 1 and diverges if p less or equal to 1. So let us see here, tabletop please. We will consider fx is equal to 1 upon x raised to p. The function f is continuous, positive and decreasing function, right? All the three properties for the function required is given. Here we will check the convergence of integration of 1 to infinity 1 upon x raised to p dx. Okay, we know that by the integral test, convergence of this integration and convergence of required p series both will happen together or both divergent together. So, here integration from 1 to infinity 1 upon x raised to p dx, it is improper integral. Therefore, we have to write as limit b tends to infinity 1 by b x raised to minus p dx. So, we can see that the next step is limit b tends to infinity x raised to minus p plus 1 upon minus p plus 1 1 to b. Here we have seen that denominator is minus p plus 1. So, definitely we have to write p is different from 1. Now, limit b tends to infinity b raised to minus p plus 1 minus 1 upon minus p plus 1. By simplification, we can write limit b tends to infinity 1 upon p minus 1 minus 1 upon p minus 1 into 1 upon b raised to p minus 1. Now, when we apply the limit b tends to infinity, in case of p greater than 1, we can see that answer is 1 upon p minus 1. If p is less than 1, we can see that it is infinity. Hence, this integration 1 to infinity 1 upon x raised to p dx is convergent if p less than 1 and divergent if p less than 1. Now, we have to consider separately for p is equal to 1. Here integration 1 to infinity 1 upon x dx for p is equal to 1. It is limit b tends to infinity log x from 1 to b. Let us put the value, it is limit b tends to infinity log b, and when we substitute the limit it is infinity. So, finally, by integral test we can say that sigma 1 upon x raised to p or n raised to p dx is convergent for p greater than 1 and divergent for p less or equal to 1. This is sigma 1 upon n raised to p dx. Okay. Slide please.